In this first problem, you see that we're trying to find out where the tangent is horizontal. Tangent, of course, tells you that you got to be dealing with derivative. So the very first thing you should be doing here is find that derivative, f prime of x. And then once we have that derivative, I'm specifically looking for where the tangent is horizontal. So that means that I want to take my derivative and I want to set it equal to 0. Because a horizontal line has a slope of 0. And then it's just a matter of solving this equation, which, yes, will require some factoring. Hopefully it's factorable so we don't have to resort to quadratic formula. Well, there's at least one step of factoring that we can do right at the start, which is we can factor out a common monomial. What can I divide out of every single one of these terms? 10, yeah. And it looks like that's the biggest number that I can actually pull out of every single term. So I'm going to factor the 10 out of everything. At least that makes the resulting quadratic in here a bit simpler to try to factor. But it does mean that, yes, we have a quadratic coefficient greater than 1. You got to deal with that. Now, any of those methods will work for factoring. In my mind, the ideal is you can do it kind of just by looking at it and kind of doing a guess and check thing, because it starts developing some kind of numerical literacy and fluency along the way. As I look at this, what I notice is the 77, that jumps out to me. So as I start thinking about factoring this up into the two sets of parentheses, I see that 77. I end up assuming that I'm probably going to have a 7 and an 11 at the end of each. And then I think about, okay, well, how can I get to 15? It's either 15 and 1 or it's going to be 3 and 5. So I'd try like the 3 and 5 in there and see, would it be 3x and then 5x? And then if that doesn't work, I'd try switching the 3 and 5. Just kind of trying some things to see if the obvious solutions would work. If those don't work, then I might resort to like regrouping or something like that. But in this case, they do work. It ends up being 3x minus 11 and 5x plus 7. Which then means that we can get our solutions by setting each of those parentheses equal to 0. So if I do 3x minus 11 equals 0, that means 3x equals 11, and therefore x equals the 11 thirds that I have right here. And of course, same basic process for the other set of parentheses as well. We're going to set that equal to 0, and that gives us the negative 7/5. All right, now with this one, are we done with this problem? In this case, we actually are done. Because notice it said to find the x values. Sometimes it's going to ask us to find the points. So there we'd have to also find the y's. But in this case, since it just said to find the x's, we're done. Which, is probably pretty good news, because trying to take these and plug them back into that original function up here, that'd be a bit of a pain, wouldn't it? Next up is a little bit of notes. Because today we're going to be taking a look at tangent lines and normal lines. And so we need to make sure that we have down the concept of a normal line. Basically, it just means perpendicular. But please add this into your notes there. And so we're going to be working with some problems here where we're going to be writing like equations of normal lines to a point and stuff like that. Now, we know how to find the slope of the tangent line, which you can actually see drawn on here as the tangent, right? Notice that the tangent and the normal line are always perpendicular to each other. Well, how are the slopes of perpendicular lines related? Yeah, so perpendicular lines always have slopes opposite reciprocals of each other. And so when we go to start dealing with normal lines, really we don't need any new techniques. We're just going to take the tangent line that we know how to find using the derivative, and then we're going to find the opposite of reciprocal of that, which theoretically we would know from geometry, but hey, that's been a few years, right? But that is where you first would have come across this. And now a reminder, which is probably worth adding into your notes as well. All right, and now to practice that idea, we're going to take a look at this situation where we're going to write the equation of the normal line to this curve at the point 1, 0. as we look at approaching this problem, if I want to know the slope of the normal line, which really is the very first thing I have to find, I'm going to have to start by finding the slope of the tangent line. In order to find the slope of the tangent line, that means I need to find the derivative. So start by please finding the derivative of this function. Alright, so when finding this derivative, the easiest part is just what's the derivative of x? That's just 1. And then it's going to be minus, now we need to do the derivative of the square root of x. And now in its current form, we can't just do the square root of it. Instead, we start by rewriting it as x to the power of 1/2. And then I can go ahead and use power rule on it. So that ends up giving me 1/2 times x to the 1/2 minus 1 is negative 1/2. But we're now going to have to be trying to actually figure out like what the opposite reciprocal of that slope is and some stuff like that. I want to go ahead and clean this up. I just think it's going to make it a little bit easier for us to look at here. So let's go ahead and clean that up. So y prime is going to equal 1 minus. Now how do I take this and write it more simplified? Well, you notice there's a fraction involved, right? The 1/2. So I already know that there's going to be a fraction in my answer with a 1 on the top and a 2 on the bottom. Where's the x going to be? The top or the bottom? Well, it has a negative exponent on it, right? And the negative exponent tells me that it's going to be on the bottom. And so that means that I have x to the 1/2 on the bottom. But again, what's an easier way to write x to the 1/2? Square root. And so then I'm going to write that then as 1/2 root x. I think that's going to just be a little bit easier for doing our computations. You technically didn't have to do this, but it's going to help us out. All right, so next up, I need to figure out what the slope of the tangent line is at 1, 0. And you might be thinking, no, we need the normal line, but no, we actually need to start with the tangent line. So to find the tangent line, we're going to take the point 1, 0, and we're going to plug that in to that equation. All right, so to find my slope now, I'm going to end up taking my x value from the original. I'm going to plug that in for x. So we're now going to go to m equals, and I'm going ahead and switching over to m because now it is going to be the slope of the tangent line. 1 minus 1/2 times the square root of 1. Well, of course, square root of 1 is 1. That's going to be 1/2 then. So 1 minus 1/2 is 1/2. Now again though, this slope, that is the slope of the tangent line. I need to know the slope of the normal line. So what will the slope of my normal line be? It's going to be the opposite reciprocal of the 1/2. So opposite means flip the sign. So since that's a positive, it's going to become a negative. And then we flip the fraction, 1/2 becomes 2/1. That's what reciprocal means. And so negative 2. So that is the slope of our normal line. And so already I know that in my answer I'm going to have y equals negative 2x. It's going to be plus b. And I still need to figure out what that b value is for my normal line. Well, I have a point that it goes through though, right? That's going to be determined by this point right here. Or we could actually even plug in those points. So 0 equals negative 2 times 1 plus b, and solve from there. And you end up finding that b is 2. And so we end up then with the final answer of y equals negative 2x plus 2. And that is our equation of our normal line through that specific point. So remember, as you're doing these, pay attention to, is it tangent line or normal line that you're being asked for? Of course, some questions might not ask you for just the tangent line or the normal. Some might ask you for both. And so there's really two problems in one here. So, again, showing you the picture, reminding you what the tangent line and normal lines look like and how they compare. Please find the equation of the tangent line through this point, and find the equation of the normal line through that point. The first step in doing either of those lines is finding the derivative. So make sure you found the derivative, and then we want to figure out what is the value of the derivative at our specific point up here. And so I'm going to take the x coordinate of that and plug it in for x in my derivative. So I'm going to be doing f prime of negative 1. And so when I do that and plug in the negative 1, I end up finding that f prime of negative 1 equals 7. Now, again, what does that 7 actually mean? What's the 7 actually represent here? Yeah, that 7 is the slope of the tangent line, specifically. So we know that the tangent line slope, that's going to be 7. Okay, so if the tangent line slope is 7, what is the normal line slope going to be? Well, it's got to be opposite, so that means flip the sign, so it's going to be negative now. And then the reciprocal, which means flip the fraction, so 7 becomes 1/7. So those are the two slopes that we were actually going for. So having done that, we're now done with the derivative work here, and we now can go ahead and go on to just finding our two equations. And so we then go ahead and figure those out. Those are our two equations. Go ahead and check that you got both those right. All right, so having practiced this work, this is stuff that we were kind of getting yesterday, just we threw in the normal line work today. We're also going to be learning one other type of thing today, because so far we've been able to use power rule to find derivatives of all sorts of polynomials. But of course, not everything is a polynomial, right? So today we're going to be learning how to find the derivative of a natural exponential function, e to the x. Now, first up, taking a look at this one, notice the problem it's asking us to find the derivative. And so if I want to find this derivative, the first thing is, can we just apply power rule to it? Well, not really. Because power rule, remember, only works and always works when it's x to the power of some number. If this was x to the power of e, we could do that, because that would be x to the power of a number, even though e is a decimal, because remember, e is a constant, not a variable here. Even though e is a decimal, we could still figure out what that is using power rule, because x is our base. But when x is our exponent like this, then all bets are off. It doesn't quite work the same way. We can't just use power rule. So we need some other way to figure it out. So to help illustrate why this is, before I tell you how we do find that derivative, I want to kind of visualize what's going on here, because you've been practicing problems like this now for a while, where we can sketch the derivative function of what we start with. And so I'm going to start by just sketching y equals e to the x, my original function. All right, so e to the x, it is an exponential again. So we know that in general the shape is going to be that sort of a thing. What can we tell? Because it's e, well, there's nothing multiplied out front of it, so it's still going to be going through the y-axis at 1. I guess we can know that much. But otherwise, notice there's no number specifically labeled on my graph here. That's because we really just want to see the sketch. And I can visualize what it's doing there. So that's the graph of our exponential here. It'd be the same if it was 2 to the x or 3 to the x, just kind of as we were visualizing it roughly here. Although the derivative will be a little bit different. But for our case here, let's now sketch what our derivative would look like. Let's start over here at the far end. If I look at that point right there, is our derivative going to be positive or negative at this point? So you notice that as I'm going from left to right there, it is increasing. Now it's increasing very slowly there, but it is still increasing. So that would be a positive slope. It's just not very positive. So that would be, a small positive number down there. All right, let's go over a little bit further. Let's say right about here. Is the slope there positive or negative? Positive. Positive, yeah. Now is it bigger or smaller than the first slope that we found? Bigger. It's still not very big in itself. It's still fairly flat, but it is a bit bigger. And so I'm going to go ahead and just sketch that in as a little bit higher there. All right, let's go then over to our axis here. My slope there, is it positive or negative? Positive. Positive. It's still increasing, right? Now, is it going to be a bigger number or a smaller number than our last slope that we found? Bigger, right? And you might be noticing a bit of a pattern here, right? Because as I continue going to the right, the slope over here, positive or negative? Positive. Is it getting bigger or smaller? Bigger. And no matter where I go over here, it's always getting bigger. It's getting to be a bigger and bigger positive number like that. And so we could just kind of rough out what it was going to look like And we could see that we just end up with a lot of points that look a lot like the original, don't we? In fact, if I sketch this graph in, it really could be the original, because remember, I'm just sketching here. The question is it actually going to be the same? Well, and the answer for that is yes. The derivative of e to the x actually is e to the x. And so notice that this should go onto your derivative rules page. You have that one page of notes, maybe 2 pages of notes reserved, where it just says derivative rules at the top. The only thing you're putting onto it is these rules. Please add this one to those rules. And as I mentioned, as we were taking a look at those graphs, we could have kind of done the same thing with other functions too, right? Like I could have done that with 2 to the x. And if I'd graphed the original 2 to the x and sketched its derivative, it also would have looked about the same. Or 3 to the x, or 5 to the x. I mean, any number to the power of x, the derivative will still look like an exponential. The question is, can I now extend this same rule where the derivative of those is just going to equal the same thing? So would it equal just 2 to the x, 3 to the x, or would it equal 5 to the x? The answer is actually going to be no. Those are not going to be the same. This rule works only for e to the x. If this could have worked for any function, we wouldn't have done the derivative of e to the x here. We would have done the derivative of like b to the x. We would have said that base could be anything, not just e. And so this rule, where it works out so tidily, is only going to work for e to the x. We will come back and see how to do these other derivatives later. And it's going to be close to this, but there will be one little tweak that we'll have to put into it. Just we're going to save that for later. We're going to get used to dealing with the e to the x's first. All right, so to practice that, I'd like you to go ahead and find the derivative now of each of these 3 functions. All right, now one thing to note here is I do have the number written out front of it. Let me bring you back to some of our earlier derivative notes, the constant multiple rule, where if I'm doing the derivative of a constant times a function, it's going to be the same as the same constant times the derivative of that function. And so when I do this one over here to find the derivative of f of x, so f prime of x, that means that the 3 is just going to hang out front. The 3 doesn't change how we find our derivative. And so I'm just doing the derivative of e to the x, which of course is e to the x. So the answer is 3e to the x, the exact same thing that we started with. So then for g prime of x, notice it's the same basic idea, except instead of a 3, it's a 0.5. So my answer will still be 0.5 e to the x. And then h of x, when I go to do h prime of x, it is not going to be e squared as our answer here. Because e squared is a number that you can calculate, right? Basically, e squared is just a fancy constant. You know, I can actually plug that in my calculator and see what decimal it equals. And what is the derivative of any constant? 0. And so because e squared is just a constant, there's no x in it anywhere, the derivative there is just 0. So we're going to be seeing the e's thrown in a lot more. But remember, the derivative of e to the x, that's e to the x. E to a number, well, that's just still a number. So that's still just going to operate as a constant. So we got to stay aware of that. And so now to continue with these ideas, now we can actually bump up the difficulty a little bit more. Please find the derivative of this function. All right, and so in order to find the derivative here, we find the derivative of each term individually. And in order to find the derivative of cube root of x, I start by turning that into x to the power of 1/3. Now you should be able to actually find that value. So then, our derivative is going to be 1/3 x to the negative 2/3 minus 5e to the x. Notice that when I took the derivative, that means I took out that dy over dx, because when I was seeing the dy over dx up here, it was meaning I still need to take the derivative of it. When I stopped writing this down here, that meant that it was the derivative. So that was equal at that point. All right, so this is actually good as the derivative, but again, I want to just keep practicing some of those simplifying skills. So let's actually clean this term up a little bit so we can remember how that's going to look. And so you notice the 1/3 is in there, so again we know that we're going to have a fraction. And where is the x going to be in my fraction? Is it going to be in the top or the bottom? Yep, it's going to be in the bottom because it has a negative exponent. That always tells me to put it in the bottom then. So the 1 is going to be on top, and the 3 from the 1/3 is on the bottom. And then I have x to the 2/3 on the bottom. But of course, I can write that more cleanly, right? X to the 2/3 is the cube root of x squared. And so then that would be more simplified. And it would still be minus 5e to the x. We could also look at rationalizing the denominator here, but I'm just not going to worry about that right now. But yes, you could rationalize it. If you went that far, you would have gotten the cube root of x over 3x. All right, so then we're just going to do one more problem, I think, here today together, and that's to combine all the pieces that we've just been. So here you have a function f of x, and I'd like to know for what x values does this graph have a horizontal tangent? Now, of course, we are dealing with a tangent, so step 1, you should be thinking about finding your derivative of the function, where you should just be getting e to the x minus 2, because the derivative of e to the x is e to the x, and the derivative of 2x is just 2. All right, now we are looking for where the tangent line is horizontal. That means where the tangent line has a slope of 0. So you do 0 equals e to the x minus 2. Now it's a matter of solving that equation for x. So I figured getting it to this point is easy enough, but then how do we solve for the exponent, right? Well, what function is always used to solve for exponents? Yep, it's going to be logarithms. And so you know that we have to have a logarithm involved somewhere here. In this particular case, because it's e to the x, that's going to be the natural logarithm. And so I rewrite this in log form, write it as a natural logarithm, so it's going to be x equals the natural log of 2. Which really is your answer, right? It's just the natural log of 2. Now you could go ahead and calculate that value as a decimal as well, but I'm going to go ahead and just leave it in exact form for the time being.